We did, of course, talk a bit about this earlier. Remember when we looked at specific questions of the type derivative times function to the power? We talked about it briefly, but let's just talk about it in more detail. The idea basically is to turn your integral into a standard integral, something of standard form. Now, standard integrals. There are, of course, the old standard integrals. Prior to 2016, yes, only a couple of years ago now, this is what we got. They gave us the good old polynomial, add 1 to the power over the power. Log. Notice how they defined it. X is greater than 0, because you can't find the log of a negative number. Exponential. And then, of course, we had our trig functions, cos, sine, and sec squared they gave us. They then gave us sec tan, and that I guess was to allow finite people in the conics when you need to differentiate the parametrics, so you can differentiate the sec. Then our inverse trig ones. Now they only gave it as inverse sine, but of course remember it could be negative inverse cos. These last couple are all to do with extension 2 techniques. So you had 1 on the square root of x squared minus a squared, and 1 on the square root of x squared plus a squared. They're pretty easy to remember anyway though, but so they were the old standard integrals. New standard integrals. So from 2016 you now get this reference sheet which has a whole heap of stuff. Just the integrals. They break it up into mathematics and extension 1. They don't have a section for extension 2. So mathematics, instead of just doing polynomial, they decided to make it as the linear function. And you remember you could add 1 to the power over the power, but then multiply by the coefficient of x on the bottom as well. The exponential, instead of just ax, they put the whole ax plus b, but still the same. Derivative over function, they're now written as the log of the absolute value of function x. Remember on the other one it said where x is greater than 0 because you can't find the log of a negative number. Well, now they've formalised it a bit more and said absolute value. So people started, of course, getting paranoid. Oh, should I be putting log of absolute value down for my answer? I suppose technically yes, but I find it highly unlikely you're going to lose a mark for not putting the absolute value in. But if you wish to, I mean, I suppose to be 100% correct, it should be log of absolute value. Sine function, again, now it's the full linear bit. And so there's those 3. And that was it for 2, because the inverse trig ones were extension 1. So in extension 1, you now see there's the inverse sine, and there's the inverse tan. And that's it. No longer listed. Sec tan, sec, those 3. So it's just something we're now going to have to just know, because we're not going to derive those each time. But if you look at the last 2, and I'll talk about it more when we get to this actual section, I guess, in the theory, then you can see the answers are pretty much the same. You know, so log x plus the square root, and the square root matches the square root underneath. Okay, now what I call the non-standard integrals. Okay, again, not listed in the old ones, not listed in the new ones. However, if you remember them, going to save you time because they come up fairly regularly. I guess this one you see, du on the square root of u, or in other words, u to the negative a half. If you think about it, u to the negative half, add 1 to the power, so the power now becomes positive a half, over the power, half, well, turn it upside down, so it's 2 root u. So I just remember, du on root u, 2 root u. That comes up a heck of a lot, especially in some of the mechanics work that we do. Du on u squared, similar one, just minus 1 on u. Because that would be u to the negative 2, add 1 to the power, over the power. Log x. No, we never integrated logs. But that actually is the standard integral for log. It's actually x log x minus x. Now, when we look at integration by parts, we'll see how that happens. But again, you don't want to do that every single time. You see integral of log x, you just know. It's x log x minus x. That's the answer. Excellent. Similar with tan x. Remember tan, we rewrote it as sine on cos. And so that we ended up then with the log of sec or minus the log of cos. It's just a matter of memorising this. And here's a handy thing to know. If you find the integral of anything with a complementary trig ratio, then its answer will be minus the complement of the original answer. So what do I mean? I want to find the integral of cot. Don't know what the integral of cot is. I do know what the integral of tan is. So I'm finding the integral of the complementary trig ratio of something I knew. So my answer is minus the complement. So in this case, it'll become minus the log, the complement of sec is cosec. Well, you know the integral of sec squared is tan, therefore integral of cosec squared is minus cot. Integral of sec, what was the integral of sec?
Sec x plus
Is it? Log sec x plus tan x. Integral cosec will be minus the log cosec plus cot. And well, there you go, minus the log of cosec, just for neatness I suppose. I could bring that negative inside and say cosec to the power of minus 1, reciprocal of cosec is sine. Make it a little bit neater. Alright, now, so we want to reduce things to a standard integral. And again, here's the difference between extension 1 and extension 2. In extension 1, they give you the substitution to use. Extension 2, you've got to come up with it yourself. Personally, I prefer the extension 2 way. Because reality, when I look at that, I wouldn't do it via substitution. Because I'm looking at that and thinking, well, the derivative of x squared plus 4 is 2x. I can create derivative function to a power. And to me, that's quicker. But unfortunately, in extension 1, they might say, do it using the substitution. Now, if they say do it that way, I've got no choice. Now, if you have to pick the substitution, it's usually the thing that's causing you the problem. Inside grouping symbols, inside log functions, inside cosine functions, things like that. So it usually will be probably, I'm thinking x squared plus 4. So when you're going to substitute u equals something, whatever's causing the problem, make that u. So u is x squared plus 4. So there's my problem. That's going to become u. I can't mix the variables. Everyone's talking about separation of variables. Whenever we write integrals down, you only have one variable. You don't have two variables in the integral. So I've got to change the x dx as well. Well, I can change the x. I can work that out. du is 2x dx. Oh, well, actually, I might use that x for the du. Because x dx, well, that's a half of du. So I can now rewrite this integral in terms of a standard integral, and this one was just the simple polynomial one. Add 1 to the power over the power. So we do that, because that's my answer in terms of u. U's a pronumeral I introduced. I've got to get it back in terms of x. So substitute back in, eventually. And there's how a mere mortal, of course, would write the answer. Us super mathematicians. Yeah. A third, x squared plus 4 root x squared plus 4 plus a constant. An alternative way of doing this one. Square root of something squared. If I've got a square root of a single term squared, that's easy to do, because square root and square cancels out. How do I change two terms into one? Trig identities. Okay, so if you see the root of a sum or a difference of two squares, you could try substituting in a trig identity. So you turn x squared plus 4 into, well, I'm going to make x equal to 2 tan theta, because that'll make x squared plus 4 into 4 tan squared plus 4. But I can change that into a single term, because 4 tan squared plus 4 is the same as 4 sec squared, yeah. So, all right. Now, my derivative, differentiate tan, I get sec squared. The advantage of making x the subject instead of u the subject, I think it can be a lot easier just to substitute straight in. Because now I'm just substituting in for x. I'm substituting in for dx. I don't have to sort of create the du now. I just substitute straight in. So, I get 2 tan theta for the x. I know it looks nastier. The square root of x squared plus 4 becomes the 4 tan squared theta plus 4. And then times the dx. The dx is 2 sec squared theta. So yes, it does look nastier. I've got 2 times 2. Square root of 4 is another 2. So 8 out the front. I've got tan theta times tan squared plus 1 we said was sec squared. Square root of sec squared is sec. Sec times sec squared is sec cubed. Oh, I forgot my d theta. Oops. So there should be a d theta there, of course. So 8 tan theta sec cubed theta. Oh my gosh, that looks terrible. Until I change it. Tan theta I could change to sine on cos. Sec cubed is 1 on cos cubed, so I get sine theta on cos to the power of 4. But sine is the derivative of cos. So I could do another substitution here. U equals cos theta. So du is minus sine theta d theta. I get minus du on u to the power of 4. U to the power of 4 is u to the negative 4. Add 1 to the power over the power. But of course that's what u is. Substitute u back in. I get sec cubed theta, but I want to get x back in. Oh, look, how do I do that? X is 2 tan theta. How on earth am I going to get sec theta? Draw a triangle. There's theta. We know x on 2 is tan theta, so the hypotenuse is the square root of x squared plus 4. Not a coincidence, you'll notice it's the same square root as right there. And I can just read off that. Sec theta is hypotenuse over adjacent. Ta-da! Same answer. I said it was an alternative way. I didn't say it was a better way. I said it's another way you can do it. Keep a mind out for that. If you see derivative times function. Derivative times function. Polynomial. X plus 1 on 4x squared plus 8x minus 7. Well, if they don't give it to me, what's causing me the problem? Probably the denominator. Sure enough, that's what they've got us to use for the u. But you'll notice the du is 8 times my numerator. So I should be able to substitute in quite nicely for this one. So it becomes 1/8 of du on u. Actually, quite nice. Du on u. So an 8th log u. Okay. What's causing me the problem? Log. We'll make u equal to log x. So du will be dx on x. Excellent. Excellent. Du on u cubed. So it's u to the minus 3. Add 1 to the power over the power. Subbing the u back in. We've got our answer. So we're just trying to get things back to a nice standard integral. X on the square root of 1 minus x. Whew, what would you make u? Probably not what you were thinking. Alright, 1 minus x is under the square root sign. So you might have been thinking, oh, let's just make u equal 1 minus x. No. We're going to make x equal 1 minus u squared and get rid of that square root sign altogether. So x is 1 minus u squared, or another way of thinking about that, u is the whole of the square root term, not just what's underneath it. Dx becomes minus 2 du. We can sub straight in. So substituting u equal to function x instead of x equal to function, domain problems, which you could have with numbers. Because square root of 1 minus x, of course, we've got problems with the domain. What's the domain of that? So that's just something to keep an eye out for. Sometimes when you do u equals, you can create things which actually don't exist because you've changed the function to something else. It's very rare, but just make that note there. All right, let's sub in. I get 1 minus u squared for the x. Bottom of the fraction becomes u. The dx becomes minus 2u du. So the u's cancel, and it's just 2 outside of u squared minus 1. Actually, quite a nice little one. So we get a third u cubed minus u, subbing back in for u. How far you want to take that one. You can factorise it, yeah. Depends how you feel that day, I suppose. Oh, back to trig. What do you reckon I'm going to make you?
Sine.
Sine. So u is sine x. So du is cos x dx. However, some other problem I got with this one. The limits. Those limits refer to x. So if I change, I've got to change those limits as well. So when x is pi and 3, u will be the sine of pi and 3. And when x is pi and 2, u will be the sine of pi and 2. Add 1 to the power over the power, substitute back in, and we get the answer. So, we got a square root 25 minus x squared. I could use that, yeah, got derivative on top. So I could use a trig function. Which way did he go? Yeah. The 25 minus x squared. Okay. So du is minus 2x dx. Got to change those limits. Working those limits out. Sub in 3, sub in 4. You go add 1 to the power over the power. U to the half. So square root of 16 minus the square root of 9, which is 1. Speaking of the square root of 25 minus x squared, which now doesn't have the derivative out the front.
And now you've got to get rid of the thing.
So, logically now, we'll do a trig one. I'm going to let x equal 5 sine u. In other words, u is the inverse sine of x on 5. Subbing in, use 0, use pi on 2. Square root of 25 minus 25 sine squared u times 5 cos u. Cos squared, oh hang on, we've got a technique for cos squared. Cos squared is?
Half 1 minus 1 plus cos.
1 plus. Okay, now sub in the pi on 2, sub in the 0, 25 pi on 4. Ta-da! Now, if they say, solve this by substitution, you have my permission to start weeping and going, oh, that's not fair, I don't want to, because that would be a silly way of doing it. Here, look at this. Square root of 25 minus x squared. Well, what do you know? Wouldn't that be a circle? And don't I have an area of a circle? Oh, a quarter of the circle, 0 to 5. That'll be a quarter pi squared. Thank you very much. And remember what integration is. If you've got a familiar shape, it's easier to use the formulas we already know. Don't forget algebraic manipulation. Oh, watch this. X cubed, the square root of 4 minus x squared. You're going to like this. I'll just rewrite that. Okay.
Oh, yeah.
Why? Because now I split it into 2 integrals. Remember, the derivative of x squared is 2x, not x cubed. But now I can rewrite this integral so the coefficient in front there is x in both of them. So now I can do each of those, add 1 to the power over the power. Voila! What I'm saying is, you can sometimes manipulate the algebra to change one integral into 2 integrals and make life a little bit easier.
What the?
Just 1 or 2 for you to do there.